as we are discussing the topics in PCA related to neural networks, let us consider the case how using a modified Hebbian update, if a single neuron can extract the principal eigen component from a stationary input. This is the sort of idea that is driving our lecture in this class. Okay. So, we start with a simple neuronal model. I have these inputs. I have an input x at time n, and x is a vector having m coordinates x1, x2, so on till xm, and I have a output y, which is basically the projection of this data vector x onto the synaptic weight connections. My w is a weight vector that has m components w1, w2, so on till wm, and my input vector x is having m components x1, x2, so on till xm. So, at the output it is basically a linear combination using these weights, which can be thought of as the projection of x on w. We assume that the input process is stationary. This is an important detail because at any time step I can get a data vector, and if I look at the possibility of the data vectors that I can get at time step n, that process is stationary. The statistics does not change with time, right. This is an important detail. Now, with these assumptions, let us proceed with the Hebbian update, right. From Hebb's learning rule, the synaptic update at time step n plus 1 is given by the weight at time n plus a quantity that depends on the presynaptic signal and the postsynaptic signal, right. I mean, there is a strong correlation. I mean, the weight would be strengthened with the correlations between the inputs and the outputs, and that is what I have here. So, Wi of n plus 1 is Wi of n plus eta, which is the learning rate, which is a small quantity, times yi of n times xi of n. So, I would make this, I would remove this subscript I here because it is a single output y, right. Wi at time n plus 1 is Wi at time step n plus eta times y of n times xi of n, right. One single output y of n times the coordinate of the input xi of n that I am seeing. Before we end the slide, a small edit here. This should be m in the summation, not n. So, we will make it m, consistent with what we have in the signal flow graph on the left hand side. Now, this update, as we see this equation, is not bounded, because if xi increases and y also increases, y increases in proportional to x, then this update becomes unbounded. The update becomes unbounded and physically inadmissible. So, fortunately, a simple solution exists to this problem, and that was proposed by Oya in 1982. What he did was incorporate a simple normalization to this update. and the normalization was done as follows. So, whatever I have in the numerator, which is w I of n plus eta y of n times x I of n, I just take sum of the squares of this quantity and then I take the square root. That means, whatever update I have at time step w I n plus 1, I normalize that vector, that is what is happening here. So, I normalize this vector at time step n plus 1, and therefore, every coordinate is having this scale factor in the denominator, right, and I do the normalization in terms of the L2 norm, right. In the L2 norm sense, I do the normalization. Now, let us explore the stability analysis of this update and see if this update gives us a stable solution and what does it reveal in terms of the analysis. So, clearly this is an adaptive system because it is, the weights are changing at every time step n, and certainly this seems to be like a nonlinear dynamical system, but let us see if it is indeed nonlinear, and that is the sort of idea where we want to drive. Now, let us consider the denominator here, right. I have a square root of summation I equals 1 to m of this quantity w I n plus eta times y n times x I of n, right. I expand this square, I expand a plus b square, it is in the a plus b square form, I expand it out, I get w I square of n plus eta square y square of n x I square of n plus 2 times eta times w I of n y of n times x I of n. So, I just expanded it in the form of a plus b whole square. Now, under the assumption that eta is a small quantity, I ignore higher powers of eta except keeping the linear term in eta, right. I can ignore eta square y square n x I square n under the assumption that eta is small and ignoring the second order and higher terms. So, what I have here is basically under the square root I have summation I equals 1 to m this quantity w I square of n plus I have 2 eta times w I n y n x I of n, right. That is the quantity that I have. Now, so let us break this sum into two parts. On one side I have summation I equals 1 to m w I square of n, and on the other side I have 2 eta times y of n, and the summation goes from I equals 1 to m. Okay. So, doing this algebra, right, let us do this as follows carefully. So, b equals my quantity summation I equals 1 to n w I square n, let me call that b. So, I basically have b plus 2 times eta times y square of n, because the summation I equals 1 to m w I of n x I of n, this is basically w n, which is basically the projection of the inner product of w with x, right, or the projection of x on w. Now, what I do is I have square root of b times 1 plus 2 eta y square of n upon b. I just remove this b factor out in the form of 1 plus some term. So, I have root of b times 1 plus. So, I do the binomial approximation for fractional indices. It is an approximation here. So, this is going to be root of b times 1 plus 2 eta times y square of n upon b under square root would be 1 plus half of this quantity, right. This is root of 1 plus 2x is approximately 1 plus half x, right, and this is what I am using here. So, what I get is root b times 1 plus eta times y square n upon b, which is the denominator term. So, denominator is basically this. So, this ratio 1 upon root b times 1 plus eta y square of n upon b can be further simplified, because now this term in the denominator, which is 1 plus eta y square n upon b, can be realized as 1 over 1 plus x, and I can use this geometric series sum to get this quantity here. Right. This is basically geometric series. So, I get 1 minus, this is equivalent to 1 minus eta times y square n upon b plus higher order terms, because now I have it completely in the numerator terms. But ignoring the higher order terms, so at this step I ignore higher order terms in eta. So, I just get the linear term which has the coefficient y square n upon b. Well, this binomial, this is 1 plus half times 2x. So, I had advertently written as 1 plus half x is 1 plus half times 2x, which is 1 plus x. Now, b is 1 because we are normalizing this, right. At every time step we are normalizing the weight vector. This is a very important detail. Norm of Wn is 1 for all n. So, doing this simplification, the denominator simplifies to a quantity which is 1 minus eta times y square of n, and y of n is basically the inner product of w with x, and that is what we try to expand it out, right. So, what I do is w I of n plus 1, I just write this equation. So, it is w I of n plus eta times y of n x I of n, which I had in the numerator in the OYAS update. The denominator, which is the normalization, just simplifies to 1 minus eta times y square of n. So, let me expand this again. So, I get terms that involve w I of n and then eta and then eta square. So, I just have 1, 2, 3, 4 terms here. So, you just do the algebra and you make a further simplification that I ignore the powers of eta, higher powers of eta square and above I ignore. So, this quantity can be gotten rid of and I can simplify this in a compact form. So, w I at time step n plus 1 is w I of n plus I pull eta y of n outside and I get basically x I of n minus Wi of n y of n, right. This is a simplified update up to a first power of eta. Clear? We have this simplification done. So, what is happening to Oyas update? Right, we had the original Hebbian update where my weight at time step n plus 1 is the weight at time step n plus eta times a measure of correlation between the input and the output. Now, with this simplification post normalization, it looks as if the input is modified as per a forgetting factor, right. So, if you just concentrate on this term xi prime of n, right, if you look at this quantity here which I call xi prime of n, xi prime of n is basically xi of n minus y of n times wi of n. So, Oyas simple way of normalizing the weight vector at every time step under the L2 norm nicely provided a sort of a forgetting term that you apply at the input with negative feedback, because if if W increases at every time step, right, you have an input which is modified in such a way that you pull this back to control by feeding yn back into the input, right. You have a negative feedback term here and that pulls down your weight from blowing up, right, and that is the game that is happening here. And this is giving rise to a stable solution under a modified or a rewritten Hebbian update that stabilizes the weights. So, Wi at time step n plus 1 is Wi of n plus eta times the output y of n times a modification to the input as per this forgetting term, right. This is very important because this negative something is giving you the negative feedback, because you are feeding back y and this is giving you stability, right. Otherwise, in the original Hebbian update the weights would blow up. We would like to further simplify, because what we formulated above was a scalar update, because every synaptic weight, that is the coordinate at the coordinate I was updated according to the rule, but now we have a weight vector that we would like to update at one time step. At a particular time step we update in one shot a particular weight vector, right. So, this weight vector update can be thought of using matrix formulation, right. If I treat x as a vector and w the weight as a vector, the whole update rule can be sort of cast in the form of a matrix formulation. So, let us see what can we do here. So, x of n is x1 of n, x2 of n, so on till xm of n. We have m coordinates. W of n is w1 n, w2 n, so on till wm n, right. These are column vectors. My output y of n is basically the inner product of x with w, which you can realize as x transpose w or w transpose x, and we will see why, which form is useful, particularly when you have to do some algebraic manipulations that can simplify your matrices in a form that that is required, right. So, you will need both of these just glaring at x transpose w or w transpose x, it is the same, it does not make any sense why we write it in these two forms, but you will appreciate this these alternatives when we involve matrices. Now w n plus 1, the weight vector at n plus 1 is basically the weight vector at time step n plus eta times y of n. So, y is my output, just to recall, eta is my learning rate, and I assume that the learning rate is constant, but in general it can be varying as a function of the time step. X of n is my input vector and w of n plus 1 is my updated weight vector. Okay. So, with these formulations, let us simplify this. Now, I plug in y of n in terms of w and x. So, I am missing a time step n here, which is sort of implied. So, w at time step n plus 1 is w n plus eta times w transpose n x of n minus w transpose n x n times x transpose n w n times w n. So, this y square I sort of realized in two alternative ways, in alternative ways. So, y of n is a scalar and it is realized as w transpose times x, and other y is realized as x transpose w. And you would wonder why I want it in this form. Recall when I look at x times x transpose, that in some sense is giving me the outer product of this data vector x, and when I take an expectation of this outer product, I get the correlation matrix. So, in some sense I have a quadratic form like w transpose times correlation matrix times w, which is more elegant than writing it in terms of x and w in an arbitrary way. Okay. So, this equation that I have above is a nonlinear stochastic difference equation. So, you see how messy things became just with a simple normalization, and if you are to implement it in the form of a code, it is very easy to do the normalization, and if it is working good in practice, then you feel happy about it. But if you were to go a little deeper and analyze why this should work in practice, then we need a lot of rigor in our analysis. Okay. So, that is what we do this, because this is a graduate level course. Okay. So, with this we will end this module and we will work further.